We're going to continue learning about the gas laws, the first of which is Boyle's law. Boyle's law pertains to pressure and volume. We know that a combined gas can be compressed. Think of like a balloon that's filled with air and it's been tied off, so that gas is confined within that balloon, and we could squeeze it. And as we squeeze it, we're actually compressing that gas. If we continue to squeeze it, we have too much pressure, and then the balloon pops. But you can actually squeeze that balloon down. Now, Robert Boyle used what's called a J tube, which is this right here, these images, to compress gases. Unlike a barometer, one side is closed and the other side here is open. So you have the chance to manipulate the pressure to see what happens to the volume. Or you can manipulate the volume, see what happens to the pressure. And so he did some experiments. And he found that the weight of the mercury in the open end of the tube will compress the air trapped in the closed end. And he had 4 findings from this experiment. He said if you increase the pressure, its volume will decrease proportionately. But he said if you take the pressure of the gas and you decrease it, its volume is going to increase proportionately. He said if the volume of a gas increases, its pressure decreases proportionately. And if the volume of a gas decreases, then its pressure increases proportionately. So there's an inverse relationship between pressure and volume. Their changes are opposite. That's what inverse means. He graphed his results where he said, okay, I have a pressure at 25, my temperature's at 10. Pressure at 50, or my volume's at 10. My pressure's at 50, volume's at 6. 100 is my pressure, 3 liters is my volume, and so on. And so whenever you graph something, you get a clear visual that, yes, this is a proportionate change. As pressure increases, volume does indeed decrease proportionately. So graphs can tell us a lot more than just the numbers because it gives us a visual representation. We spoke about kinetics, and now we're adding some gas laws to that. So we know temperature plays a role in kinetics. So if the temperature of a gas is constant, that was one thing that Boyle maintained. He maintained that constant temperature. And we compress that gas, the pressure must rise. So if we decrease the volume by compressing it, its pressure is going to increase. He developed a mathematical formula for this. P1V1 equals P2V2. You will need to know this. So let's do a practice problem. And as we read, we're going to underline some key words. It says the maximum volume a weather balloon can reach without rupturing is 22,000 liters. So this right here, we're talking about volume and pressure. So we're going to say volume equals 22,000 liters. That's the maximum. It is designed to reach an altitude of 30 kilometers where the pressure is 0.0125 atmospheres. So we have a pressure of 0.0125 0.0125 atmospheres. What maximum volume of helium gas should be used to inflate the balloon before it's launched? So we're looking for what the volume would be. If we're launching, so this is V launch, this is, we'll say 30 kilometers. We'll say that's a mountain peak because it's pretty high. So this would be up in the mountains and this would be up in the mountains. But launching, what's the pressure where it would be when it's launching? Where do you launch a balloon? You launch it where you are, which is typically sea level, the Earth's surface, which would be 1 atmosphere. So this you had to do a little extra thought and say, well, where are we? What's our air pressure where we are? Just presume if it's not given to you that you're at sea level and you're just going to use 1 atmosphere. So now we have our formula that Boyle developed. P1V1 equals P2V2. If we want to solve for V2, we need to go ahead and set that up now. You could do it after you plug your numbers in. It's a little bit easier if you solve prior, but either way is acceptable. So P2 times V2, but we want to get V2 by itself. Well, if we divide by P2 divided by P2 is just 1, so it cancels out. But if we divide on the right, we have to divide on the left. So now we have P1V1 over P2 equals V2. So now we can solve for V2. We have V1, P1, and we have P2 here. So let's plug it all in. So V2 equals P1 to 0.0125 atmospheres times 22,000 liters divided by 1 atmospheres. My atmospheres will cancel out. So my V2 equals 0.0125 times 22,000 divided by 1, which equals 275 liters. I know word problems can be a little overwhelming. That's why I suggest underlining what you see and writing it down. Always try to piece it out. If I don't write it down, I'm going to get lost. So that's why I write everything down. And that's why I use different colors too. So here, if this were a little confusing the way I wrote it, I also have it digitally here. We have the volume at sea level, pressure at sea level equals volume at 30 kilometers and pressure at 30 kilometers. I solved for the volume at sea level, plugged it all in, and we get 275 liters, just like we did before. Now, we have another practice question. We have 2 liters of air. So first volume I'm given is 2 liters at atmospheric pressure. All right, so P1 then, we'll say 1 atmosphere, are compressed into the 0.45 liters. Well, that's the second volume I'm given. So that's 0.45 liters of a warning horn. If its temperature remains constant, what is the pressure? of the compressed air. So what's the new pressure? So we know we have P1 V1 equals P2 V2. We want to know what P2 is. So if I want to know what P2 is, I have to get it by itself. To get it by itself, I am going to divide that side by V2, because V2 divided by V2 is 1, and it cancels out. If I do that to the right side, I have to do it to the left side. So now my new equation is P1 times V1 over V2 equals V2. Now I can plug in my work. My V1 is 2 liters. My P1 is 1 atmosphere. And my V2 is 0.45 liters. My liters will cancel out. That leaves me with atmospheres. So 2 times 1 divided by 0.45 gives me 4.44 atmospheres. So P2 is 4.44 atmospheres. If you have questions, let me know. I know math can be a little bit hard for some, but practice and meet with me if you need extra help. Okay, that was Boyle's law. Now we're going to talk about Jacques Charles. He was another scientist, and he investigated how changing the temperature of a fixed amount of gas at constant pressure affected its volume. So he's looking at temperature and volume. And he states that at constant pressure, so pressure has to be constant, the volume of a gas is directly proportional to its Kelvin temperature. It has to be in Kelvin. So this means if you look at this chart that he charted with all of his data, that pressure's constant, the volume is directly proportional to its temperature in Kelvin. So as the temperature increases, the volume will increase. If the temperature decreases, the volume will decrease. And you can actually do this with a balloon. You can blow up a balloon, and if you put it in the freezer, and don't blow it up too high because it won't fit in your freezer, but if you blow up a balloon and you take a measuring tape around it and measure it, and then put it in the freezer for a couple hours, take it out, and you can measure with the measuring tape the circumference again, and you'll see that it's changed, that the temperature has changed. We're still at atmospheric pressure, but we dropped the temperature, so the volume's going to drop. Now, his mathematical law is written like this. V1 over T1 equals V2 over T2, because remember, they are directly proportional. They're not inversely proportional, they're directly proportional. We're going to stop there. And if you have questions, please reach out to me.